All right, this is video 2 for section 12.1. In hindsight, I probably should have just finished off the video because I don't think there's that much left, but whatever. You'll have a longer one and a shorter one. Okay, so last time we talked about the distances. So now let's go ahead and, skipped the bottom part. So now let's go ahead and actually just put it into use real quick. And we'll see if we can actually find the distance between two three-dimensional points and different places on the graph. So let's find the distance from the point 3, 2, 1. So it's definitely something in the first octant. And we'll find the distance from that to the origin. That one should actually be very simple to do. For letter A here, we want to find the distance between 3, 2, 1 and the origin. Well, if we're using the origin as the second point, 3 minus 0, 2 minus 0, 1 minus 0, that's just 3, 2, and 1. So a distance from something to the origin is the easiest one to do. It is literally going to be, in this case, the square root of 3 squared plus 2 squared plus 1 squared. So that's going to be, what, 9 plus 4 plus 1. So that's going to be 14, so square root of 14. That is the distance from the point 3, 2, 1 to the origin. Hopefully that makes sense. Now I want to find the distance from 3, 2, 1 to the x-axis. Well, that means that I want to go from the point 3, 2, 1 down to the x-axis. Well, if I'm going down to the x-axis, the only thing that has any kind of distance, because I'm hitting the x-axis itself, as a matter of fact, here, let me kind of sketch what this would look like. We're going from the point 3, 2, 1, so 1, 2, 3, 2, and then up 1, out 3, over 2, out 3, over 2, up 1. So something like this. I'm going from that point to the x-axis. Hopefully what you can see here is, because the straightest distance, or the shortest distance, excuse me, from a point to any place is a straight line, so it's going to go straight to there. That would be the straightest distance. You're not going to go at an angle. I'm not going to go from that point to the origin. I'm not going to go from that point way out here. That doesn't make any sense. I'm going to go as quickly as I can. So really, I'm going to the point 3, 0, 0. So I'm going from the point 3, 2, 1 to the point 3, 0, 0. It is the closest way to do it. So if that's the case, then my distance formula here is going to be 3 minus 3 squared, which is 0, 2 minus 0 squared, and 1 minus 0 squared. So without writing the entire thing out there, I'm going to get the square root of 0 squared plus 2 squared plus 1 squared, which is going to be the square root of 5. Okay, and in part C, we want to go from the point 3, 2, 1 to the point 2, negative 7, 5. Again, this is just go ahead and we will write this one out. So basically it's the y2 minus y1, x2 minus x1, z2 minus z1 kind of a thing. So let's see, the x's, the difference in the x's here is going to be 2 minus 3 squared plus negative 7 minus 2 squared plus 5 minus 1 squared. So that's going to give us the square root of 2 minus 3 is negative 1 squared is 1. Negative 7 minus 2 is negative 9 squared is 81. And 5 minus 1 is 4 squared is 16. So we should get 82, 88, 98 squared is 98. And that is perfectly acceptable as an answer. You could simplify that because 49 is a perfect square, which goes into that. So that would be 7 root 2. Square root of 98, 7 root 2, exactly the same answer. The only reason you would ever have to give me 7 root 2 is if I told you to simplify completely. Otherwise, root 98 is perfectly fine. And then the last one, we want to go from the point 3, 2, 1 to the xy plane. Well, let's look at our sketch over here. The point 3, 2, 1 to the xy plane is basically straight down. Not really a lot of work to do there, because really all you're talking about is what is the z distance from 3, 2, 1 down to the origin, or down to the xy plane. Well, it's just 1. The z distance literally is 1, because that's what, that's what that value is right there. So again, you could plug it all in, but again, we are going from the point 3, 2, 1 down to the xy plane, which is the point 3, 2, 0. So it's literally just a z distance of 1. All right, now let's go ahead and talk about how this works with planes. So what you can do is you can kind of think of a plane as a three-dimensional version of a line. In 2 dimensions, both x and y have a power of 1 to be linear. 3D, exactly the same thing, it just extends to z. So now we have a z value as well. So two-dimensionally, if I wanted to draw the equation x equals 3, well, that just passes through 1, 2, 3, and then it's a vertical line. 2 dimensions, that's x equals 3. I probably should not have made that dash because it is a solid line. So there's x equals 3 in 2 dimensions. Not as easy to draw that in 3 dimensions because it does form a plane. So in 3 dimensions, here's my z-axis. I'm going to draw my x-axis a little bit more vertically and my y-axis a little bit more out to the side. You may not notice a difference there, but I certainly do when I do it. I just do my angle that I'm looking at the XYZ plane a little bit differently. So now we have to find x equals 3. Well, that's still the same place. 1, 2, 3. So here's x equals 3. Biggest thing is that this is no longer just a line. We can draw a line to start with. So here I'm going to dash it just to give some perspective. Stay parallel to the y-axis. Man, this is horrible. And it extends off in both directions. Now, again, we cannot actually extend this because it's a plane in every possible direction. There's just no way to do it. So all we're going to end up doing is drawing basically a snippet or a piece of this plane. Well, the plane does extend. It also extends not only in the xy plane, it extends in the z plane infinitely. So stay parallel to the z and draw yourself, some kind of a vertical. What is going on here? I have no idea how I just did that or where that green line came from. And then again, try and stay parallel to the y-axis best that I can. Something like that. So that hopefully gives you somewhat of a perspective on your plane. And again, this would actually technically extend down below the XY plane and above the XY plane and left and right, goes on forever. There's just no way for us to physically draw that. So it's just kind of a snippet of that plane. So again, hand-drawn x equals 3 in 3D is not the best because it lacks depth. So it's not going to be easy to see. The use of something called WinPlot, which is something I use, I'm actually going to cross that out because I prefer, and I don't know whether I used it with you guys last year or not, but I prefer this thing called CalcPlot 3D. And you will see me use that throughout the year when we get to things which are really hard to visualize. So I will be using that program. But if you know how to use it or have looked at it, by all means, go for it. It's a great thing to plot some three-dimensional stuff. All right, so that graph was a good thing to start, but let's look at something a little bit more interesting. How about the plane y equals x? A little bit harder to draw this one than it was the other one. So once again, I'm going to try to do this. Let's see. I'm going to draw my y-axis more horizontally this time and more vertical for the x. Let's see if this works. I hope so. So here's x, here's y, here's z. We know that y equals x, a 45-degree line between y and x. So it's going to look something like this. It's going to extend in both directions. And then when we want to draw the vertical piece of this, again, just stay parallel to the z-axis, and then stay parallel to the y equals x line, And it looks something like that. That's actually probably one of the better jobs that I've done. But hopefully there you can see how the plane cuts right through, and the z-axis is included in the plane, how it cuts right through the 45 degrees of x and y. All right. How about the graph of y equals 5 plus x? Well, again, the best idea is to sketch our three-dimensional plane. And again, I'm going to try and draw the y a little bit more, horizontal. Now, in this case, I do know I'm going to have to extend out in that direction, specifically on the x, because that's where it's going to intercept the x-axis. So I do know that this thing, y equals 5 plus x, if I were to sketch this, first of all, in the two-dimensional xy plane. So here's our xy plane. This thing has a y-intercept of 5 and a slope of 1. So a y-intercept of 5, 1, 2, 3, 4, 5. It's got a y-intercept there, and a slope of 1 means it's going to go up 1 over 1 in the positive direction, but it's also going to go down 1, left 1 in the negative direction, which means that it has a x-intercept of negative 5. So right about there. So now I can go ahead and sketch through there something which is going to go out in this direction. And then again, staying parallel to the z. This one's much more difficult because of the angle. And then stay parallel to the line that we just drew. And hopefully you can kind of see how that one stands up vertically, crossing through y equals 5 and x equals negative 5 on the xy plane. You guys will get used to all this sketching because you will have to do this stuff eventually on your own anyway. Good visualization stuff here. All right, one more of these sketching of the graph. This one's definitely a little bit more challenging. It's x plus y plus z equals 1. In order to sketch this one, we're actually not going to sketch a rectangular area just because it's not as easy to do. I mean, you could, but in this case, again, it only has to be a part of the plane. The easiest thing to do here is to find all of the intercepts. So let's go ahead and find the x, the y, and the z intercept. Well, to find the x-intercept, you plug in 0 for y and z, which gives us an x-intercept of 1. Put that right there. To find the y-intercept, you plug 0 in for x and z, which gives you a y-intercept of 1. Likewise, to find the z-intercept, x and y are 0, which gives you a z-intercept of 1. So really, what we're going to sketch here is a triangular region of our plane, because the easiest thing to do is to sketch this portion of the plane, which crosses through those specific points, the x, the y, and the z-intercept. Now, again, you could try to sketch this thing and extend it out in all directions as a rectangular thing. That's fine too, but it's not necessary. That's the portion of the plane that we would probably be interested in. All right, so there you go with your x, y, and z-intercept form of doing that. One more thing to talk about, spheres. So a sphere, its two-dimensional counterpart is basically a circle. So a circle is the set of all points that are equidistant from a given point, and that's what we call the center. So think about it. Every single point around the perimeter of a circle or around the circumference of a circle is exactly the same distance from the center. That is the definition of a circle. A sphere is exactly the same thing. As a matter of fact, when we say that for a circle, we're technically not really telling you the truth, because that's really the definition of a circle. Of a sphere. It's actually the set of all points equidistant from a given point, where the distance from that center is what's called the radius. Notice we pretty much defined exactly the same thing for the circle and the sphere. Technically, what we should say for the circle is within a plane. A circle is the set of all points that are equidistant from a given point within a given plane. Has to be in the same plane. We're not limiting it with a plane for the sphere, so That's what the sphere's definition is. So recall the formula for a circle with center h and k is given as x minus h squared plus y minus k squared equals r squared, where r is the radius. This is derived from the distance formula, which we did in the very beginning of class. It's just the distance, again, from the center out to any point on the circle. This is exactly the same idea as it is for a sphere, so all we're going to do is we're going to add in the z component, which in this case we use L for the z component, and z, of course, is the actual point on the sphere. So the distance formula is the equation of a sphere in 3 dimensions. So the equation of the sphere is going to be x minus h squared plus y minus k squared plus z minus L squared equals your radius squared. That is the equation of a sphere. Basically, it extends from the distance formula in 3D, so it's very easy to figure out. All right, that's it. That was actually longer than I anticipated, so I'm glad that I went ahead and did this. This is probably one you could have fast-forwarded a little bit through, but there you go. You have enough to do the stuff for 12.1. Any questions, bring them to me in class. Good luck.